Good afternoon, everyone. My name is Yiting Wei, and I'm from Heidelberg University Eclectx team. Today it's my great honor to be here and introduce our latest work to you, Hybrid CNN Transformer Model for Accurate Classification of Human Attention Levels using Workplace EEG Data. So my presentation is divided into 5 parts. Let's begin with the introduction. In nowadays information-driven world, the attention has become one of the most precious and limited resources. Maintaining an appropriate attention level is key to enhancing work and study efficiency. And it is also a crucial part for safety risk prevention, and continuous attention detection supports health management, especially for the elderly. So right now, existing method for attention assessment is mainly for 3 methods. And firstly, we can use video and image to monitor the attention. It is non-intrusive and real-time. However, it is highly sensitive to privacy concerns and strongly rely on the environmental conditions. Apart from that, we can also use the behavioral features to analyze. The good thing is that you can integrate it in your daily work. However, it is highly indirect and could be easily affected by the individual difference. Also, we can use questionnaires to do self-assessment. It is very simple and low cost, but it is highly subjective. So combining with nonverbal objective continuous monitoring's advantage, physiological signal-based method has become one of the most promising one. So among all these effective signals, EEG has been widely recognized as the most direct and sensitive approach, providing with rich brain activity information. So what and why is EEG? EEG records the weak electrical signals generated by the activity of cortical neurons in the brain. And attention is a cognitive state that is closely associated with neuroactivity in specific brain regions. And this electrical signal dynamically changes along with variation in cognitive state. In this way, we can link EEG and attention together. So by analyzing many papers in this field, we found out that the key challenge in our field is mainly focused on 4 paths. Firstly is the limited classification granularity. Like most studies, they only use 2 to 3 attention levels, which limiting sensitivity. And the second part is that the data often collected in the controlled setting, that lack of real-world validation. And third part is that the EEG itself, the signal is noisy, non-stationary, and highly individual. And last but not least, most of the work, they highly rely on shallow machine learning or handcrafted feature that limited them to capture like more deeper information in the EEG signal. To address all this about challenge, we propose a multi-level attention classification method based on hybrid model combining CNN and transformer architecture. And we also validate the method in a real-world workplace environment. So let's go for the dataset part. We collected the data by ourselves and it's called OEEG. And from figure 3, you can see the device that we have used in the experiment for collecting the one-channel EEG signal. We together recruited 10 volunteers and conducted 14 days experiment. And for each subject, they need to do 10 times data collection. And for each collection, it lasts for 1 hour. And during this time, the volunteers, they just need to do their daily work as usual. And after finishing the collection of the signal, they need to finish the 6-point Likert scale questionnaires. And this number will be used as the future label. So let's go for the key part of our proposed method. Firstly is the pre-processing of EEG signals. We will apply forced order Butterworth filter to remove low frequency drift and high frequency noise. And then we will use zero-phase IR notch filter with bidirectional filtering to remove high-line interference without phase distortion. And then we will divide EEG into non-overlapping 16-second windows. And then we will use short-time Fourier transform, SCFT, to convert each EEG time window into a 2-dimensional spectrogram in order to capture both temporal information and frequency domain features, and also provide image-like inputs for CNN model. And here from figure 6, you can see our proposed hybrid CN transformer architecture. And I will introduce some details here to you. So for the input, it is a 2-dimensional EEG spectrogram, and we design a multi-layer of the convolution layer. So for the first layer, it is focused on extracting low-frequency oscillation features, and for the deeper, they are used for extract higher level and cross-frequency interactive features. And we also use the max pooling at the first 2 layers to prevent overfitting. And after we get the convolution output, we will reshape it into a token sequence and then apply sinusoidal positioning encoding to inject temporal order information to adapt it to the transformer. And for the transformer block, it is a 4-head multi-head self-attention mechanism, which can model long-term dependencies and capture global patterns. And then using the pooling and fully connected layer, we can get our 6 attention level classification output. Then is our experiment and results. So for the data preparation, our total sample is 20,016. And we divided our data set randomly in a ratio of 70%, 30%. And we also do the 10-fold cross-validation and apply 4 kind of evaluation metrics. And here you can see the confusion metric results from figure 7. And we can tell from it that for the extreme level, like level 1 and level 6, it can reach pretty high recall, which is 96.03%. However, for the intermediate level, it shows misclassification. And these errors reflect the difficulty of distinguish subtle cognitive difference. So the trade-off between granularity and discrimination is a key challenge. We also we do the per class classification results from table 1. We can also get the conclusion that also for the extreme level, they perform the best. But when it comes to level 2 to level 5, it shows lower performance. And it is mainly due to frequent misclassification between adjacent level where cognitive state difference are minimal. And also the intermediate level remains challenged and still need improvement. We also do the benchmark comparison, and from table 2, you can see the macro average metrics for 6-level classification across our proposed model, a baseline CNN, and 2 comparison with that method. So from the result, we can see that for the traditional method, they can reach the reasonable accuracy, but lack fine-grained discrimination. And they only rely on the handcrafted features and simple classification rules. And for the baseline CNN, it's truly do some improvement, but lacks global sequence modeling. And our proposed methods, by overcoming all these shortcomings, it achieved 87.37% accuracy and superior performance across all metrics in 6-class classification. So the last part is for a discussion and conclusion. So for the key findings, this paper proposed a 6-level attention detection framework, which can effectively capture subtle attention state change, suppress noise artifacts, achieve 87.37% classification accuracy, and also demonstrate strong detection for extreme attention levels. But for the remaining challenge, we should focus on how to improve the prediction of the median attention levels. And also the individual difference and dynamic environments are another 2 key parts for us to find a solution to do with it. So the conclusion for this paper is that the proposed method enables fine-grained 6 levels attention detection and shows strong potential for real-world cognitive monitoring. And we also achieve significant improvements in accuracy, robustness, and scalability. For our future direction, we will introduce personalized model or domain adaptation to solve the individual difference problems, and we will also explore generative models and leverage multi-model fusion techniques together into more application scenarios. That's all for my presentation, and here's the link for the website and paper if you are interested. Thank you so much for listening.
Thank you. Do we have any questions? Yes, right here.
So, are you planning to test this with more electrodes or different locations? I don't know which was the location of the electrode.
You mean the experiment location?
The location of the EEG electrode.
Yes.
Where was it exactly? Was it frontal?
On the head, like it is a headband, and it is one channel EEG.
Okay, and where exactly is the electrode placed?
You mean the sensor?
Yeah.
I think it's around here. Yeah, it is a headband and it's a sensor.
Are you planning to look at more locations in more electrodes? Or?
Yeah, this is an interesting part. But for us, like why we designed this experimental is because we want to test it in the workplace. So for us, if the device is more simple, it is better for the officer to work with and to collect the data and monitor their daily work like attention level. Thank you.
Any other questions? Yeah, right in the back.
So why did you choose random cross-validation? And don't you think there's a risk for implicit overfitting with very short segments of 16 seconds, not being able to verify out of distribution generalization?
So you mean why we randomly like choose the divide the training set and data and test set? Well, actually, for now, we don't do the individual modeling for right now, but actually, the difference between our work and other works is that we get the more precise granularity, like from 1 to 6. And we fuse them together, and we also do the tenfold cross-validation to see the results and do the macro average. So from the result itself, it works to trust, but we will definitely do the what you have mentioned, like individual evaluation later in the later work. Thank you.
One more question?
For the you mean the exact method for tenfold cross validation?
Yeah.
Actually, we randomly divide our data sets into 10 parts, and for each time, 10% of it will be used as the test set. And and for the 10 times other 9 parts, they will be formed as the training set.
I think we can take this question after the session. And I do have a question, we have some time. So, do you have any hypothesis as far as why attention mechanism improves the accuracy in the case of classification here?
So you mean that...
You implemented self-attention, so why do you think it makes it work better? Improves the accuracy.
You mean the attention and work efficiency, the relation between themselves? Between these two? The attention and work efficiency.
I was talking about the transformer.
Yeah. You mean how this model will improve the accuracy of attention assessment?
Yeah.
Yeah, okay, thank you. So actually, when there is some medical work saying that when your attention level change, then it will reflect in the EEG signal, maybe short-term change and long-term range change, like the trend in long-term. So for why we propose this hybrid CNN and transformer-based architecture is because it can, like CNN is more good at like extracting the low-for patterns, and transformer can can evaluate the long-range dependencies. So if we combine these two together, then maybe we can show this inner connection between this long-term and short-term change in the EEG signal.
Great, thank you.
Thank you so much.